So, a big part of the semester is already over. We already covered topics for the discrete case, that means for proposition logic, and for linear arithmetic, real and integer arithmetic. Looked a bit at decidability. And before we go to the nonlinear case, we look at some applications. Some means two. First, we look at bounded model checking, and then we will look at another example of creating, basically counterexamples. Both methods are for creating counterexamples. That means you have a system, and you model this system, and you can model check. You can analyze some properties formalized in some logics. And if this property does not hold, then it is important to give back an information where the mistake in the system lies in. So in general, this is given in passes or traces of the system. And bounded model checking is one method that uses subsolving for generating counterexamples. It can also be made complete. That means that you can also use it for verification. But first, we look at the counterexample generation part. So, we take the simplest systems that we can imagine. These are Kripke structures. Kripke structures consist just from a set of states. These are discrete states, like S1, S2, and so on. There are transitions between them. They can be labeled. I skipped the label because it is not important for us. The labels can be taken for synchronization purposes. That means you can build also paracompositions of Kripke structures. And now there is something special by these systems. They are labeled. We have a set of AP is used usually for atomic propositions. And we attach to each state a subset of these propositions. For example, in S1, A is attached in S2, A and B. I assume you already heard about Kripke structure, all of you. Is it the case? Is anybody have never heard about Kripke structures? Okay. So these are models used to model real systems. And you can see that these are rather simple. They are just, you have states which are black boxes. You do not have any variables. So you must distinguish between state transition systems and transition systems in general. In state transition systems, you have just these black box states and transitions in between. That means if I'm in, for example, state S0, then my system can execute something and get thereby to state S4, for example. But it can be that this thing that is modeled here is a program. So that means the program executed a single atomic assignment and got from one state to another. But if I want to analyze the program or show that the program has some properties, usually it is assigned to the variable values, for example. I want to show that it is never the case that x is 0 because I will divide by 0. So how can I do it with these systems? What can I model with these systems? Because obviously I cannot write variable values on, for example, transitions. And therefore I have these atomic propositions. So what are these? A could be an atomic proposition. Let's say x is not 0. But this is now not a formula in linear arithmetic over the integers, but this is a string. That means the systems are made simpler. I remove variables, I remove all the states. I just model the flow of control between the states, but still I need some information about the states in order to express something, to formalize that, for example, I want to prove that x is never 0, and I do certain work already by the modeling or by the generation of this model, in that if A means x is not 0, then the modeler defines this labeling function assigning properties to states. And he assigns by the modeling that if the system is in state S1, then x is never 0. So we assume a priori that this atomic proposition labeling is valid. And then we try to talk about these systems. So these are Kripke structures. Formally, a Kripke structure is just a tuple, a finite set of states. This can also be extended to infinite ones, but we cannot handle infinite ones by bounded model checking. Then we have an initial state. We have a unique one. You can also have non-deterministic systems in that you have several possible initial states. We have a transition relation. As I mentioned, it can also be labeled. I skipped the labels. And we have this labeling function where we assign to each state a set of atomic propositions. Now, how do we interpret this set of atomic propositions? Those atomic propositions which are in the set hold, and those which are not do not hold. That means I do not assign negated properties to the state. Okay, these are Kripke structures, and they have a syntax that we have seen on the previous slide, and they also have a semantics. And the semantics is usually given in form of passes. So we start, let's say S0 is the initial state, then I start in the initial state, make one transition, get into the next state, and thereby I get state sequences such that they are connected by transitions. And basically the behavior of a Kripke structure is given by the set of O passes which start in its initial state. Basically the semantics talks about infinite passes. We can also take finite passes by just taking a finite prefix of an infinite pass. And if we have a finite path, then we can also define its length by the number of states in it minus 1. So the number of transitions actually along the path, along the finite path. Then we will use some auxiliary notation, P of j. With that we refer to the j state in P, and P with lower index j will mean the postfix starting at the state P of j. That means I remove the first j states from the path. And then if we look at the passes, what you can see, we have this example for a Kripke structure, and what is its semantics? It's all passes. You can of course take also a set, but you can also look at it as a tree because it is a non-deterministic system. So we start in this case in S1. I think it was called perhaps S0 previously, I don't know. So this is the initial state S1. This is here. And now the system is non-deterministic by going either to S2 or to S4. That means now I have here this possible choice, non-deterministic choice, going to either S2 or S4. In both, I have just one single possibility to continue for S2, and for S4 also I can go only to S3. And once I'm in S3, I have again the choice going either to S2 or to S4. So instead of looking at it as a set of passes, we can look at the behavior as a computation tree. Now to describe properties of such systems, we can use these labelings on the states. And we have different logics. Perhaps you already heard the word temporal logic, where temporal relates to time, at least to discrete time, where something holds. In the logics we described until now, you can only talk about one assignment to the variables. That means just one state. Yeah? You can say, for example, x plus 0 equals 1, and this is satisfied in the state where x has the value 1. But now we have computations. That means we need sequences of states. And for those, we need different logics. These are called temporal logics. And they can tell something like, there exists a path such that it is never the case that C holds. Or there exists a path such that eventually we reach a state such that from this state all possible continuations satisfy always A. Or things like that. These are called temporal logics. And they are classified into two groups, linear temporal logics and computation tree logics. Linear temporal logics talk about single passes. That means they cannot express like there exists a path such that somewhere I come to a point where for all passes that continue. They must not switch. They always talk about one path, and thereby the strength of this logic is that you can express their Leibniz properties. The other class, branching time logic is called. It is where they can talk about branching, but they cannot fix to one single path. That's why you can express safety there. And then you have a kind of union where everything is allowed and you can talk about everything, and this logic is called CTL star, computation tree logic. Star means arbitrary alternation of quantifiers. There you can express both. What we look at today is linear time logic. That means we talk only about passes and not about branching. And I told you that this logic talks about passes, but what we looked at until now did not talk about passes. So we will need some kind of transformation. And this is the example. So we will use proposition logic. We will encode this logic, which we introduce now, into proposition logic and use subsolving to search for counterexamples in Kripke structures specified by such linear temporal logic formulas. We could also use more expressive models and also more expressive logics, for example, by talking about time. These are a more general transition systems. They are called hybrid automata, or especially this is only rectangular automata. And if we can do the same for these systems, bounded model checking, let's say just for reachability. That means checking if we reach some critical states there, because now we have, here firstly we have continuous behavior, so you have a kind of clocks, and these develop linearly. That means what you reach after a certain time you can express in linear real arithmetic. So if you make bounded model checking for these systems, then we can transform it to SMT sat modulo linear real arithmetic. But this is actually the same way, but a bit more complex. That's why we take this more simple case for Kripke structures. I already told we deal with linear time temporal logics, and the syntax looks like the following. Probably you know this is just how you define abstract syntax. Anybody not knowing this notation? So we have this A is atomic propositions, which we attach to the states. Then we have conjunction and negation. That means we have also all the other syntactic sugar like disjunction, implication, if and only if, and so on. We have two temporal logic operators, next and until. Next means it is satisfied by a path if in the next state it is satisfied, and until means that this first operand must hold until after a finite number of steps the second gets valid. Finally, and globally as syntactic sugar, you can express it with the other ones, that's why they are green. And finally means after a finite number of steps something happens, and globally means it holds along the whole path. Some examples. Next time, the first path satisfies next time P, because if we start in this state, then at the next step P holds. But the second path does not satisfy it, because if I stay here, then in the next state P does not hold. For the until, P until Q means that after a finite number of steps, Q will hold, and P holds all the time before. It can also be that it holds after 0 steps. That means the formula is also satisfied if it holds immediately in the first state, independently whether P holds there or not. And it is not satisfied if either Q becomes valid at some point, but there at some point before P gets invalid, so P gets invalid before Q gets valid, or if P holds all the time, this is the last example, but Q never gets valid. So in these two cases, the until formula is violated. And for syntactic sugar, eventually means after a finite number of steps, P gets valid. And it doesn't matter what was before. And the only case where it is not satisfied is P never holds. That means it is a negation of globally not P. And globally means, globally P means P holds all the time, and it is valid, it is violated if at some point P does not hold. Whereas note that these formulas can be also nested. So this semantics gives us a recursive definition. So I can, in linear temporal logic, also test something like globally P until A until B, and for all passes, something like this. So I can nest formulas. For all is implicit. I do not have quantifier in LTI because I talk about passes, but implicitly we will see that a Kripke structure satisfies an LTI formula if all passes satisfied. So we have an implicit for all quantifier at the beginning. So formally, the semantics is a pass satisfies an attribute proposition if this proposition is in the label set of the first state. This is the labeling function. A pass satisfies the conjunction if it satisfies both operands of the conjunction. It satisfies the negation, a negated formula, if it does not satisfy the non-negated formula. A pass satisfies next time phi if this means now the subpass starting at the first state satisfies phi. It satisfies the until operator if the second operand is satisfied after a finite number of steps and the first operand holds all the time before. And eventually and globally, actually, we do not need to define because these are syntactic sugar, but sometimes it is used to use as normal elements of the language. So eventually, if you want to define the semantics, means that as there exists a state along the path such that the path from this state on satisfies phi, and globally phi means that it holds for all states. And you see now the problem is this semantics talks about passes, and we want to break it down to propositional logic. For that, first we formalize a Kripke structure satisfies the property, and as I said, it is the case so a property holds for a Kripke structure if all infinite passes satisfy the property, and it violates, it is just a negation, if there exists an infinite path which does not satisfy the property. And now the trick is, what we use is that also finite passes can violate or satisfy a property if they contain enough information to assure that there exists an infinite path. So assume, for example, we have a path and it satisfies eventually A. Then of course there is a finite index where A holds, and already on this finite prefix we already see that eventually or finally A holds. This is for validation, for negation. If we have a path which violates globally A, And also there is a point where A does not hold. So also this prefix is already a counterexample for globally A. What we will use as an additional trick is you can, of course, also prove that for a path globally A holds. But if you consider a finite prefix, then basically you never know what comes afterwards. So that's why it is hard to prove globally properties by finite passes as proof. But if these passes contain a loop, so if you find a path which has a loop at the end, so the same states are repeated over and over again, and you say, show, for example, that the prefix to the loop and one looping satisfies the globally, then you know that it is satisfied along the whole path. So we will distinguish between finite passes which do not have a loop and which have a loop. That means you have a finite path where from the end you come back to the state before, and then we can encode the satisfiability or violation of LTI properties on finite passes. And why do we need finite passes? Because we can encode finite passes by a finite number of propositional variables, and then we are back at propositional logic. So model checking was first done by enumeration. That means all the states are enumerated, and there are efficient procedures how we can label states with LTR formulas or CTR formulas for branching time. And this is very efficient for smaller systems. The problem with model checking is the state space explosion. That means if you model systems where you model really each state on its own, assume some program with interleaving, the number of states is really very huge. So this system becomes extremely large, and that's why if you build the whole Kripke structure explicitly, then the bounds of model checking are given by the number of states which must be handled. So then the next step was to introduce symbolic model checking. Symbolic means that we do not explicitly list all states in our transition system, but we use another encoding. One possibility are BDDs. These are binary trees such that you can encode n states by log n variables. You can also encode functions by BDDs. And they are more space efficient, but the problem is that now the efficiency goes into the computation of the BDDs. So firstly, you can represent the BDD. Let's assume we have just a Kripke structure with two states, just to express, give you the impression how it works. So the BDD approach. Assume you have, for simplicity, just two, just this Kripke structure. Very simple. Here A holds, here B holds. Then you can use just one bit to encode in which state you are. Let's say this is bit S, and if S holds, then this is state S1, this is S2. If S holds, then I mean that I'm in S1, and if S does not hold, then I mean that I'm in S2. Yeah, if I would have 4 states, I could use 2 bits, because with 2 bits I can encode again 4 values. And now I can build up a BDD that encodes that S1 is the initial state. This BDD has a variable order. Basically, it is just S in this case. I have a node S, and if the value is 1, which is denoted by a solid line, then I go to a leaf which says that this is true, and if it is 0, represented by a dotted line, then I go to the so-called 0 leaf, meaning that the value of this formula is false. So I have a set of variables, and each path assigns a value 0 or 1 to this variable, so only Booleans, and each pass leads either to a 1 leaf or to a 0 leaf, telling thereby if this assignment satisfies the formula or not. Perhaps I make another example because you look still a bit skeptical. We encode a formula. Let's say a proposition logic formula A or B, A and B, or C. Now what do? I have an A node. It can be true or false. If A is true, then either B is also true and the formula is true, or B is false, and then either C is true, then I go to one leaf. Actually, I have only one leaf and one 0 leaf. Or if C is false, then the formula is false. And if A is false, then independently of B, depending on the value of C, if C is true, the formula is satisfied. If C is false, then not. Yes, so this is a BDD encoding this formula. And the same way, I can this one here just encodes the formula S. S holds because this is the initial condition. Initially, S must hold. Yeah. So the next point is I have the triplet structure, the initial state, and now I need the transition relation in order to have passes. So the transition relation contains just S1 to S2 or S2 to S2. So first, this was the initial condition. Now the transition relation between S and S prime. That means when I can go from S to S prime by a transition step, S, if S is true, then I'm in S1. Then the transition relation holds if afterwards I come to S2, that means S prime is false, then there is a transition. If S prime is true, if S prime is true, then there is no. That means S1 does not have a self-loop. This is this path to 0. And if S is false, then S2 has only a self-loop. That means S prime must also be false. Must also be forced to have a transition. And if it is true, then there is no transition. This is the transition relation. So now I coded the whole system. I have the initial state in a BDD and a transition relation in another BDD with prime variables. And now, if I rename, for example, this transition BDD, in that I rename S to S prime and S prime to S double prime, then I can make a conjunction of those two. There are operations on BDD, conjunction, disjunction, negation, testing for emptiness, and these operations can be done. And then I just make the conjunction of these two. Then I eliminate, eliminate the variables in between. This is not because I cannot write, but this is because at the side. Eliminate S prime, and then I will have a transition BDD from S to S double prime. That means I have the pairs which are reachable in 2 steps. And then I can continue it by taking new steps and new steps until I do not see any new states anymore. So this you can use for model checking to collect all reachable states. It doesn't matter if you don't understand it completely. The point is that these operations, like conjunction, can be very expensive, and the sizes of the BDDs can increase hardly, and it strongly depends on the variable ordering, which you already have seen in subsolving that the variable ordering is crucial in some cases. So for the right variable ordering, you find the solution very fast, and with the wrong one, you compute very long. So if I go back to the previous slide, this was this symbolic model checking approach. So you do not enumerate all states anymore, but you compute with sets. And the problem is here, this is from the memory here, from the memory more efficient, but it can be time consuming. And then bounded model checking was introduced. And this was the time where the subsolvers were so fast already and so well developed due to also industrial support. In industry subsolving, basically the industrial application of subsolving is since you can do bounded model checking, because bounded model checking encodes the passes, like for Kripke structures. What is used in industry is not so much for Kripke structures than for circuits. If you have some hardware which you develop, then you can use the same approach that we talk about here for the Kripke structures to encode the input-output behavior of circuits, and then you can at least search for bugs in hardware. And the earlier stage you search, if you find a bug, the cheaper it is to remove the bug. So bounded model checking means that we encode finite passes of a system in a certain formula in a logic, in our case propositional logic, and this formula will encode that there exists a bad path which does not satisfy our specification. So we encode the existence of a counterexample of a certain length. If we start with length 0, it is unsatisfiable, means that the initial state is not buggy. Then we have lengths 1, 2, 3, and so on. So we search for longer and longer counterexamples, and it is in general incomplete, but you can extend it for certain systems with some additional conditions that you know where you have to stop. So for example, if you analyze reachability, then after you have path length, the number of states, then you know if you didn't found until then something, then you will never find anything. This diameter can be reduced. We will look at the end how to do it. Okay, perhaps I will just show now the structure of such a formula. So what we have is a Kripke structure, an LTL property, and what we search is a counterexample. And bounded model checking is a technique to search for finite counterexamples, not only for Kripke structures, but we look at for Kripke structures. And here's an example. So if you have the property globally, finally A, that means never mind where you are in the system execution, in the future A will happen after a finite number of steps. This is a special or typical Leibniz property. That means if it does not hold, then there exists a path such that finally you reach a state where A never happens in the future. So in our example, if you start in S1 and then go to S4 and then you loop here forever, then A will never hold. So obviously this Kripke structure does not satisfy a property, and this infinite path is a counterexample for this property. And we can observe that this infinite counterexample can have a finite representation because you have a loop from S3 to S4 and back. So this basically this prefix already can already be used to encode this infinite counterexample. Okay, and how it goes in detail we will look at next week. Thank you.